going to bring Tyson back in now. Tyson's going to give us a bit of history lesson on all the history of this and how we got to where we are.
Yeah, thanks, Frank. Yeah, so part of wondering where the future lies and how we're going to get from here to there is actually taking a little step back and looking at where we came from and where databases evolved from. IBM really put out their RAMSAC system back in 1959. And why that's kind of key for databases is that was the first random access tape drive that they built. And so the random access piece gave way to being able to randomly access data in different places rather than sequentially, which computers had only been built for sequential access up to that point. So Dr. Codd in 1970, he's a fellow at IBM. He actually wrote the paper and was the father of the relational data model. That gave way to, and sorry, folks, a little technical difficulty. That gave way to the entire birth of what we know today as the relational database system or database management systems. SQL came out of that in the late 70s, different languages. The standard came out in 84. During the 80s, you had the emergence of all the commercial ones, DB2, Oracle, Sybase, and Formix. Little tidbit, and Formix was my favorite database that I used early on in my professional career. Personal computers then were actually had their own databases in the 80s. And so you see this evolution of concept into production. And during the late 80s and 90s, relational databases exploded in private businesses. I mean, the adoption of what it means to have a 3-tier network of data, business logic, and presentation really took hold there. Then in the 90s, you start seeing some new twists on relational databases. The object-oriented database came into being in 1990, just as object-oriented languages were hitting their stride. Then you start seeing where the evolution today occurs. In 1998, the first reference to NoSQL by Carlos Strozzi in a paper came out. Then you start seeing the evolution of key value pair document stores, wide column databases, graph databases. In 08, Neo4j, one of the front runners in the graph database technology today, their first implementation was 08. By 2010, you see that all the commercial databases have consolidated. Some have gone out of business, some have consolidated into a handful of companies, and there's a couple of popular open source MySQL and Postgres being them. And then, of course, I would be remiss in saying that part of this whole big data evolution is the blockchain part of it that comes into play. And then 2016, BurstIQ's Burst Chain with data on blockchain emerged. So this is kind of the history of where we're going, where we've come from. And the industry has been evolving very rapidly. I mean, I know this is 50 years, but within 50 years, a lot has transpired and a lot has been learned. And then with the advancements of computers, like Frank said, Moore's Law, decade after decade, things are improving faster and faster. We are generating data in ways that we never imagined before. And so databases are going to become key, and there are different tools for handling them. And we're going to jump into that in the next set of slides. So just as a kind of a breakdown for those that are a little unfamiliar with the types of databases, what I was referring to when I said RDBMSs or DBMSs, I was referring to the actual table that we call, or databases that we call SQL databases. Now, SQL databases are very table oriented. So if you've ever opened Excel and worked on a sheet, on a tab at the bottom, and you created multiple sheets, you're in essence working with a primitive database where each sheet is a table. And you can make relationships between those tables. You could say this row refers to this row. And if you're a real Excel expert, you can make workbooks do some crazy and amazing things. Well, that's just like what you do in a regular RDBMS, but RDBMSs are at a much larger scale. But the idea here is that you're creating constraints by tying tables together using what's called a primary key and a foreign key as indexes to one another. And again, that works great to a certain extent. But the evolution of NoSQL actually encompasses columnar databases, column-wide databases, key value pairs, as well as document stores. They all fall under the umbrella of NoSQL. And in fact, one of the key technologies we're going to get into here real shortly, which is really fun, is graph databases. And depending on who you listen to, they technically fall under a NoSQL umbrella. I like to think of them as a little different. They have a very different flavor to what they do to the data than NoSQL and SQL do. NoSQL lacks kind of that third normal form structure that most data modelers and data architects adhere to when they work with RDBMSs. And that's a good thing, because now you can start exploring different types of relationships. You're not bound to the hard and fast of a table. Then we get into graph. And this is where we're going to spend a bunch of our time today. Graph databases aren't really focused on a table or a group of data. They really focus on what a node is. And a node you can think of as a noun. And we'll get into a little bit of this in a second. And then they're tied together by verbs or relationships. Now, this adds a whole different type of structure to data than a relational database does. And I'll show you on the next slide what I'm referring to. Now you can see that anybody who's done any kind of computer science work and understands data structures has seen a graph before. And if you haven't, I'm sure you're on Facebook or Twitter, or you've seen a diagram of like a molecule or something, and you start seeing how atoms or cells have bindings and relationships to one another. You see how you get that notice on LinkedIn where it says, hey, you're a third relation to this other person. And if you've ever wondered, how on earth do they know that Maria has a third relationship to Jim? Well, it's probably accomplished because of graph database structures. So each of these hexagons is a noun. It's a person, place, or thing. It's an entity. And an entity is referred to as a node. Now, we can give these nodes labels or categories. And in this example, I highlighted that this node is a person. And so we have 4 people on this graph. Their relationship to each other is how they happen to know one another. Now, this is a very simple graph, and it's also known as a directed acyclic graph because it never circles back on itself. And it also, it gives us the ability to ask questions of data in a context not available in RDBMS. And let me give you an example. If I have a table in a database of people, and I have another table that has relationships, if I want to see who Anne is related to, or what she has a relationship with, like 2 or 3 generations away, I have to write a kind of an inner join query back on one table 3 or 4 times in order to resolve all the possible combinations of where Anna may know someone. Well, in graph database structure, I can simply ask, how does Anna know anybody 2 or 3 degrees away from myself? And that's a very, very simple query for a graph database to execute. And so when you start looking at data in this context and you start putting relationships around data, and what I don't have on here is a more complex example where I might have medications. And now I have where I can see that Tom and Maria are taking the same medication, or perhaps they see a doctor that's related to another doctor. So I can start making lots of inferences on the types of relationships that are kind of buried and hidden in traditional databases, but are very obvious and explicit in a graph database structure. And so when we get into some of the machine learning topics here a bit, you'll start seeing how graph database structures can actually aid and give us deeper insights into how machine learning can use that data versus a normal database. So Frank, you want to take us to the next one? So I started talking about this, and I'm going to give you a little bit of foreshadowing at the end of this slide, because Frank's going to talk about something that is really key to what we're trying to really do with data in today's world, and especially at BurstIQ. But first of all, graph database strengths. Again, I've kind of alluded that instead of having data that you loosely couple together through IDs and primary keys, and how do I make multi-dimensional relationships, that's really hard. Graph database does is directly and connects the data right off the bat. And so you get that binding immediately and you get to understand it. The thing it does though, is it allows non-DBAs and data science professionals to really use visual tools and write different queries to understand data in ways they couldn't before. And so it's the idea of narrowing the bridge between data science and data consumers. And graph databases have a lot of technologies there. We won't get into that quite today. That's a whole nother fun topic that we can explore sometime. So what all of these items do is add context to data. And context of data has value that is very hard to quantify in words for you right now. But when you start adding context to data, how does this data element relate to this data? And what are some of the other contexts of why this exists here? You start opening up all new realms within machine learning.